Hi, friends. It's Mr. Rogers, and today we're going to go over three of the cell receptors and cell signaling. But the first one we're going to go over is G protein. And so I'm hoping you can see my screen here. You can see the G proteins that I drew. Technically, there are supposed to be four pictures, but I just did it in two just to make it a little bit simple, and so we can explain it. So the first thing about G protein that I want us to know is it involves um, it's not just one ligand. There's multiple kinds of G proteins. So let me put multiple kinds of G proteins. Now, why I want to make sure that's clear is I don't want you to think like this is the only shape of a G protein that exists in the world. I want you guys to know that, this for this purpose, we have this one, but it looks different. The main concept of G protein, though, why it's called G protein, is not so much what the actual protein looks like, it's this process down here. So, what happens is the first thing is we have a ligand here, a signal. And the signal is going to come in. And once it comes in and it attaches, it's going to allow, this is a protein enzyme, it's going to allow this phosphorus to attach to this GDP. Now, the big question is, what is GDP? And the answer is quite simple. GDP is the same as ADP, and GTP is the same as ATP. It's just instead of adenosine, it's guanine. Okay. And so it's just a different nucleotide as the part of ATP. So when we went through ATP, we talked about the fact that it's basically an adenosine attached to three phosphates, like that. Well, GTP is just a different shaped guy right here. That's all. Okay, don't get confused by that. So once this ligand comes in, a phosphorus joins, and this becomes a usable energy molecule. And this usable energy molecule then moves across to a set spot, almost kind of like a train car on a track. It can't just like go this way. That's impossible for it to go this way. It's set to travel on a set path. Now, if you really wanted to know, the path it travels on is set up by the cytoskeleton. And so it's set up by things like, honestly, it's going to be mostly microfilaments is what is going to give it its path. Okay. Just so you're aware. So this is going to move across this GTP. So it's going to be a GTP. And it's going to move, and it's going to end up at an inactive enzyme. And once it hits that inactive enzyme, it releases its energy and it changes the shape and that starts the cascade is the word that we're going to use, or it's going to start the process of sending the signal to wherever it needs to go. Okay. Now, this whole setup, there's some flaws here, and so we're going to talk about that in a second. But there's some good things. First, this is a medium speed, medium success. Okay. And what I mean by that is it takes its time. It takes some time because obviously we have to have the signal come in. The GDP has to be turned into GTP. It has to travel a set distance to an inactive enzyme. It has to activate that enzyme, then starts the cascade. This is not instantaneous. This takes time to do all these steps. And so it takes some time. It's not as slow as maybe another one that we're about to talk about, but it does take time. And it has medium success. There are flaws here. So first, sometimes the ligand can't fit or can't find. So not every single G protein, every single of these proteins are everywhere in the cell membrane. A cell might only have a couple. Sometimes ligand can't find the one it needs to connect to, or two, there could be an issue with either the signal, it being made, maybe it was made improperly, or the protein doesn't have the right lock for the key to fit into. Okay. Another issue we could have is GTP doesn't travel to right spot. So maybe the GTP doesn't actually get to where it needs to go. Maybe it goes this way, even though it's not supposed to. Things happen, or maybe it gets off track and goes this way. There are issues there. There can be issues there. And then finally, the last one that could go wrong is that we could have a problem with the enzyme. It doesn't start cascade. So these are not common things. These are not common problems, but they can occur at times in your cells. And so this is a medium success, medium speed. So this is a common thing. G protein is the most common of any of these receptors types because it works pretty well. I mean, it's not perfect, but it works. And it has medium speed, so it gets jobs done. Now, there are other situations where we need it to go faster. There might be other situations where we need to make sure that we always succeed. And so we have the other two types for that. So this is the most common. So I'm going to put that up top because that's important. Now, again, all cells are going to have this. All cells in the whole entire earth have this setup. And so the other interesting thing is when G proteins are the most common, you can probably find out that when poisons or medicines or other things, a lot of things evolve to mess with the G protein setup. Like if I'm going to mess with a bacterial friend of mine and I want to screw up what they're doing, maybe I create a signal that blocks their G protein or a signal that sends through the G protein and screws up what's actually supposed to happen. Or maybe I create a venom or poison that blocks this from occurring because everybody's got a similar setup, so it works with everybody. So that's something to think about. G protein's most common. These things here, these pictures here, you should have 4 technically, but I just did 2. I hope G protein made sense. We'll keep talking about it in class on Tuesday. Have a wonderful day.